Okay, so today I would like to continue to finish the syntactical analysis just to see how we can write valid formula. But we're going to talk about its meaning maybe after the break. We'll see how much we can go after the break. But let's finish the remaining part about syntax, one thing at a time. This very quick recap about what we did last time. If you remember this single slides, that's all you need to know about parsing for this course, especially we're learning about formula. Later on, we're going to learn about another logic language for temporal logic called CTL that also requires certain syntax to be understood. So LTL is a very good example for us to get trained by reading grammar. So we learned mostly about drawing parse tree, right? You can definitely refer to the exercises we did, especially you want to consider also operator precedence whenever you want to draw the parse tree. Similarly, at the end, we introduced about the leftmost derivation. For that one, you also need to know about the parse tree. Also need to know about the operator precedence before you do it. Let's now continue with it, and the next one will be rightmost derivation. It's also very straightforward. Let's now just get it done. So this is where we were. Let me just bring you up to speed from last time. We have the start variable over here for the grammar. That's where we start. Okay, and every time you want to go ahead to do the derivation, you have to make sure you choose the leftmost non-terminal. To start with, this is the only one, so that, of course, is the leftmost. And then you do phi implies phi, and what's the leftmost? This one here, and etc. All right, that's what you said last time. I presume you're okay with it. And of course, like the case where we draw the parse tree, you have to make sure you also box the subformulas over here in a way that correspond to the operator precedence. That's also what we talked about last time. If you got any trouble understanding the basics, let me know. Right? You definitely need that for later assessment. All right, let's now just continue from here to finish that. You can imagine that ultimately, very soon, I'm going to put a single page for the same string. We're going to look at its parse tree, leftmost derivation, and rightmost derivation to see how they compare to each other. That'll be the concluding remark for this exercise here. We'll get there very soon. All right, so now how do we continue from here? First of all, you want to ask yourself, are we done with the derivation? Apparently not. At least, if you got at least one non-terminal, you're not done yet, right? Now we got 1 and 2. Which one should we choose? Of course, this one here, the leftmost. Right, that should be clear to you. Let's now just continue from there. So we're going to choose the leftmost non-terminal. So that can be derived to FP and, so what should this part be? So that will be the right-hand side of the conjunction. That should be G something, right? So G something will be some rule over here. So that'll be G phi, and then implies phi. All right, are we okay with the first step? That's just how we continue from last time. Okay, just make sure you're okay. And then, let's continue. This will be the leftmost. And that one should be derived into the Q. And we do have some base case, any atom, right? And if we do that, it's going to be F, and then P, and then G, and then we're going to get Q. Implies phi. And of course, the next one to really handle will be, this will be the leftmost. And we can expect that this guy here is ultimately going to be derived into this one. All right? And let me make it more spacious so we can just make it completely done. Oops, let me do it again. How about just this part? That should be good. Okay. Make it much smaller. All right, like that. Okay, let's continue. Don't worry, if I ever ask you to do that in the exam or in the written test, you will get enough space in the box. Okay, let's continue. How do we do with this one here? This phi here should ultimately be some P until R. Exactly over here, right? So what we got is we got FP and GQ implies phi U phi. That corresponds to exactly this one here. And then we are going to do this one, leftmost. That one there is going to be F, P, and GQ implies, this one here would just be the base case, right? P, U, phi. I think I got just enough space to finish the last step. That'll be the leftmost. We got only one left. Of course, if the until part, the right-hand side is more complicated than this, you have to do more steps. It depends. Let's finish that. F, P, and G, Q implies P until R. That's it. You can see the final form over here is one where there's no non-terminal. That means you're done. When there is no non-terminal, that means you're done. Okay, it's not difficult, as you can see. It's just a little bit tedious to do. Right? It's some process you will need to know how to do it, and that's it. Any question about this one? Good. And for your exercise, I got one here, and one here. Let me give you a little bit look ahead if you want to do it. Apparently, you can see the way you're going to analyze the operator precedence will be a little bit different. So that means the corresponding parse tree or leftmost derivation or even the rightmost derivation could be different, right? Just a little bit look ahead. So I will leave that to you. 2, 3, and 4, leftmost derivation. If you got any trouble, let me know. Maybe a little bit later, I will also give you the solution. But I would suggest you try first. You definitely need it. Otherwise, you wouldn't know how to handle that during the test. All right, the final one will be the rightmost derivation. And that one there is actually going to be just the same as the leftmost derivation, except that we have to make sure every time you want to handle some phi that's non-terminal, find the rightmost one. That's the key. To save everybody's time, I would suggest we look at the solution directly. Okay? So we can spend a little bit more time on the more interesting semantics part. Okay, let me show it to you. Just for this one here, okay, you can focus just on, try to just omit this part just for now. Okay, I'll show you quickly. This will be the rightmost derivation for this first formula. Why is that rightmost? If you take a look, we start with the start variable. Apparently, that's the rightmost automatically. And then we do the implication. And then in the case of leftmost derivation, we should really derive this first. But now, in the rightmost derivation over here, we're going to select this one here. That one is going to lead us to, you can see this part here has been turned into this part, which corresponds to this one here. So we're handling the consequence of the implication first, right? Hopefully, so far, so good. And then this one here, we're going to handle the rightmost again. This one here, that'll be the rightmost. This will be the rightmost, and rightmost. And the final form over here is one where there's no non-terminal. Okay? The overall picture is you want to make sure every time you want to derive, choose the rightmost non-terminal. All right? Are you guys okay with this? Yeah, Chidalu, please. Yes.
For example, in the, I guess the binary operator, like
yeah.
You're doing leftmost or rightmost, why don't we just like put the two variables in at the same time?
At the same time. It's a very good question here. So I think that the spirit about doing derivation is to really see how you can do in a consistent order. So there is another definition about how we can prove a grammar is actually ambiguous or not. But that's not something we're going to cover in this course. But for this one here, just by definition, when you want to do derivation, you want to do only one step at a time. Pretty much like in 1090. If you want to prove certain theorem, sometimes your professor might just tell you that you should not skip any steps. Only one axiom or theorem application at each step. You don't want to do more than one.
I guess that's just how we do it because it's kind of confusing because there's no such thing as like one.
Sure. So let me make it a little bit simple for you. In case I say you got to do rightmost derivation or leftmost derivation, in that case, no way around. You got to do one step at a time. On the other hand, if only for your informal sketch to see if any derivation is possible, yes, you can make jump step just to see. That will be okay. Good. Patrick?
Are any of these better than the others? Or is it kind of just
Nope.
our choice?
Very good. Very good question. Patrick's question was, this versus this, leftmost, rightmost, is there any argument of which one is better? No, they're equivalent. As long as you're consistent. What you really don't want to do is like this. Maybe up to this point, I'm doing rightmost. Suddenly, I decide to change to leftmost. Ultimately, it might still be okay, but for some more theorem arguments for later, but which we wouldn't cover, that's not good. You always don't want to have a consistent ordering. Yes?
Just like one more question. So I guess, so what do you conclude from doing this? Like, what's the conclusion?
Conclusion is, very good. Because for every derivation step, for example, we go from here to here. Oh, let me use the example here. That's easier to see. I'm going to write it down too. Every single step for the derivation is based on some grammar rule over here. So if you can go from here, the start variable, to any formula that has no non-terminal, that means this string formula is considered as syntactically correct with respect to this grammar over here. Okay, let me write it down. So it's really important. Each step of derivation is based on a rule in the grammar. Pretty much like when you try to do proof. Let's say you got 10 lines of proof. Each line is based on some axiom or theorem. If you can go from the beginning until the end and every step is valid, the final proof should be valid. Similar idea. Okay. All right. All right, that's very good. And let me do a final comparison for you guys, and then we can conclude about this syntactic analysis. This guy here is the rightmost, This guy here is the rightmost derivation. And this one here is the leftmost derivation. Let me be a little bit more explicit. Okay. So now this will be the leftmost. This is the leftmost start variable. Leftmost, leftmost, leftmost. This one, leftmost, leftmost, and leftmost. And the final one here is exactly just the same because we're doing for the same string. Doesn't matter if you do the leftmost or rightmost derivation, you end up in the same string. Because we assume our grammar is actually unambiguous. That's something you can assume always for this course. All right? Yes?
Is it because leftmost equals rightmost, that means that's how you know the grammar is unambiguous?
Not that simple. So for now, let's not go too much into there. You can assume that any grammar you might be given for this course, actually you only be given the grammar for LTL and also CTL. You can assume that they are just unambiguous. Oh, sorry, it's not intentional. I always didn't see you. It's actually exactly my blind spot. Sorry about that. Go ahead.
I was just wondering, because you said we do this course, we're doing the boxing based on precedence.
Yes, yes.
When we do the boxing, wouldn't that make, because we've already enforced an order, so wouldn't that make the leftmost derivation always be the same as the rightmost?
Okay. So again, the reason that we have to do the boxing is grammar we are is somehow simplified without embedding the operator precedence. You're going to consider that separate first. So you always consider operator precedence, box and components, and then based yes, the final product will be the same thing, yes. Given that the grammar is unambiguous, if you look at, we start from the same thing here. Intermediate steps are kind of different because you can see what we highlight over here is different, right? But the final product over here will be always the same. Yes, absolutely. Yes. Also similarly, if you look at the leaves of the parse tree correspondingly over here, that will also give you the same string as well. Okay. All right, there's one more comparison I would like to make, just to see how we can consider these three notations together. Okay, let's say this. Let's look at the parse tree first. If you look at this subtree, okay, this one here. Okay, this subtree here, let me write it down. this subtree really corresponds to the antecedents of this particular formula, right? That one is F, P, and G, Q. First of all, are we okay with that? Right? This subtree. And what's more important about it is, you can see given that this is a subtree, this is also a subtree. They have a common parents over here. That means if you actually want to somehow figure out the order of interpretation, you should really consider interpret this first, and then the symbol followed by the consequence over here. This in order over here. Can you see that kind of ordering in the derivation? The answer is yes, but not as nice as a parse tree. But I would like to point out to you, so you can try to find other example yourself too. Right, guys, let me repeat again, right, just in case you get lost. When you circle any subtree, for example, over here, that tells you that the subtree itself must be interpreted as a whole before you can move on to its sibling on the right. That's okay. No worries. Okay. So here, that will be antecedents, right? And then followed by that, you got to consider the consequence, okay? How do we see that from the leftmost derivation? Okay? Can you guys identify which fragment of the leftmost derivation will correspond to this particular left subtree? Let me be a little bit more precise. Let's say this is step number 1, step number 2, 3, 4, 5, 6, 7, 8, and 9. I'm pretty sure Patrick knows the answer, but anybody else? Thomas, go ahead. From which, how many steps? There should be a multiple step that will correspond to that particular subtree. Which steps? Not just a single one. There should be multiple ones. Okay? Absolutely. Absolutely. Sorry. So let me be precise over here. Let me box that first. Okay. And let's see why.
What's wrong with step 1?
Oh, it's mainly about step 1. Step 1 is actually where you actually start to really work out exactly how to derive it.
It's kind of circled in the subtree.
Yeah. Yeah, I agree. Let's not be. I agree. Think about this part over here is where we find this a non-terminal over here. Exactly. And then this part over here is exactly when we got the next one to handle will be this one here. That means we're done with Q and P. Q and P over here. Jora, are you okay? Good. I want to make sure. Ed, are you okay for you? All right. All right, guys, for example, if I simply circle another subtree, will you be able to identify where the corresponding step is, derivation? Just make sure you can do it, all right? Any repetition will be needed for you? Chidaru.
You said you circle something to identify where in the formula it is.
Exactly. Yeah, that could be one question. Yeah, for example, here I circle this particular subtree over here. That one corresponds to exactly what we want to do over here. Mm-hmm. Right. Yes, we're going to look at that. Yes. Mm-hmm. That means this entire operation over here ought to be considered as the ought to be considered as the antecedents of the implication. That's exactly what we're doing here, because starting from here, we have the antecedents being the non-terminal. At the end, we have the entire antecedents work out without any non-terminal, right?
How does this work with the rightmost derivation?
It will be the.
Does it work?
It also works, but the order is a little bit reversed. Let me show to you. Okay, let's box that first. How do we see the corresponding steps in the rightmost derivation, right? It should be, let's see over here. Yep. Oh, sorry. Oh, sorry, let me. Absolutely. Thank you. Yeah. Just make sure you be careful when you box it. Absolutely. Right? If you look at this one here, up to here, what we have done was we just try to, so up to here, we have just done with the consequence. So antecedent is left, right? Starting from here, we try to work out exactly what the antecedent is, right? So that means this part here tells us the antecedents should really consider as this part over here. Because ultimately, this one over here will correspond to this one over here. That's basically what we are doing. All right? That's how you can see the correspondence.
It's the same thing except the right-hand side.
Yeah, exactly. So, yeah. In the leftmost derivation, we try to work out this one first as a whole before we try to work at this. In the rightmost derivation, we try to work out exactly what this is before we try to do this part over here. There's just suggestion about what should you really consider as a whole for either the antecedent or consequence. Okay? So what should you know? Number one, given the string, how you work out the operator precedence, number one. Number two, how do you draw the parse tree? Number three, how do you do LMD? Number four, how do you do RMD? Number five, if I circle a particular subtree, are you able to identify exactly where they correspond to in the steps for either this or this? That's all you need to know. I even lose track, right? But don't worry, Chidalo, refer to the recording. Okay. Let me repeat once more. Let me not say number one or number two. That will confuse everybody. You want to know how to work out operator precedence, right, to box the formula. And then you want to know how to draw the parse tree. You want to know how to do LMD. You want to know how to do RMD. You want to know if I circle any part of the parse tree, what will be the corresponding steps? And, Chidalu, vice versa. If I tell you this is what I want to look at, what will be the corresponding part in the tree? That can be also.
But are all types of boxing valid subject? Are all box possibilities?
Yep, absolutely. That's really, okay, to be more precise, the boxes we're doing is actually identifying subformula. That's also something we need to do. That will be the next topic, some brief one. Yep. To be more precise, this one here, little box, is a subformula. This is just another subformula. And this whole thing here is just another subformula. Jora.
So we wanted to identify part of an LMD that corresponds to the
Subtree.
Yeah, so if we wanted to move for the rightmost child of the root, would it be,
Oh, you mean this one here?
yeah, for that, would it be 6, or would it be 5 to
That would be
6 to 9?
something like that, yes, from 6 to 9. Yes, exactly. Starting from here, being the non-terminal, yes, that's right. Yeah, I'll give you guys maybe a little bit more example so you can work on. Yes.
Just out of curiosity, is there any relationship between like the parse tree and then like what's it called, like pre-order traversal in converting that to
Okay, sure. We wouldn't really talk about traversing the tree to process the tree actually in this course. But of course, back in your 2011, you can definitely do pre-order or post-order. Maybe not in order because the tree is not necessarily binary. So if you do pre-order or post-order, that might correspond to some order you want to process the tree. But let's not get there. We don't really handle that. If we need to, I'll give you some concrete example. Yeah. All right. That might be what TLA plus have to do behind the scene to somehow parse the formula, of course. But we don't need to worry about it. All right, guys, any question? Are we okay? All right. I believe there's one more thing, something about subformula. Okay, exercises. Yeah, I'm going to give you some solution a little bit later. And that's another exercise for you, okay, just to draw parse trees and derivation. Subformulas, very quickly. And subformulas, the definition is very simple. Basically, identify how many subtrees are there in the parse tree. And then you will see that it simply corresponds to the individual boxes we have identified using the operator precedence, like what Chidelo just mentioned. How about you guys do very quick parse tree for this particular formula? That'll be one more exercise for you. Okay? You guys do this, I'll put it on my iPad. How about that? And you can compare. Let's take about 1 to 2 minutes. This one, hopefully, is not too bad because we actually got quite many parentheses to actually help you, right? Just imagine if you didn't have the parentheses, how would you do it, all right? All right, let me draw the parse tree as well, and then we'll compare. Which one? This one here?
It says not to, right? Would that be an atomic operation, or would that be?
Okay, think about this as atomic, and then we're applying negation to it.
Okay.
Yes. Yeah, of course, when you parse that, you got to parse that into, yeah, by using steps, yes. Yeah, give me a moment. Let me finish that, and then I'll talk. Give me one moment. Okay, I'm almost done on my part, so hopefully you guys are getting close. Okay, I believe I'm done, but guys, take 1 more minute. Take your time.
Like you said, introducing brackets doesn't count as an operation.
It does, yeah, parentheses that we introduce shouldn't be included as part of the parse tree. It shouldn't be. Yeah. Sorry?
They're implied as part of the grammar.
Guys, what about 30 more seconds, and then we'll compare answer, all right? Hopefully, if you're finding that you're quite slow in doing this, maybe it's a good time to actually try to practice a little bit more, right? And then I'll talk about subformula, which is a very easy concept. Alrighty. All right, does it agree with yours? Patrick, maybe you can tell me. Okay, good. Good, guys? Anyone who got a question about the parse tree? I presume you guys are okay, right? Drawing the parse tree is something we covered already. Now, how do you see the subformula? There are two things over here. I can even tell you the tip if I asked you this in the test. If I simply ask you how many subformulas are there, what do you count?
All the internal phi's.
Yeah, just count how many phi's are there.
Do we include the
Indeed.
subformula?
Yes, indeed. Because remember the definition for a subtree. Is a tree the subtree of itself? Indeed. So we are just being consistent with 2011. Question?
We also include like P's of first twice.
Yes, yes.
So we include it twice, right?
Include what? Sorry. Oh, no. We only, okay, let me say this. First, there are two questions here. Let me put it down. Number one, how many subformulas? In that case, you just count how many phi's. How many? Let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Awesome, 10. That will be one question I can ask, right? That one is easy. You don't need to enumerate explicitly about the subformulas. And question 2, what are they? What? How about numerate? Numerate all subformulas. Okay. Well, of course, at least you know there should be 10. If you miss any one of them, at least you know you're not really getting there. Okay. Well, be systematic. You know, you want to go from the largest one to the smallest one, or want to go from the smallest one to the largest one. Doesn't matter. Let's say we want to go from the smallest one to the largest one. First of all, I will choose This one here. Okay, how about this? Let me number them. That'll be easier. 1. I'm numbering the 5s over here. You can see 1, 2, 3, etc. How about 1 here? 2 over here. 3 here. 4 here. 5, 6, 7, 8, 9, 10. So there should be 10 answer. All right? Let's be very systematic. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the actual test, you don't really have to put these numbers out. You don't have to. I'm just showing to you how you can work it out. All right? What about the formula corresponding to 1? Don't write phi p, just p. All right? What about number 2? GR, which correspond to this guy here, right? It's a subformula, a components. Number 3, R. Number 4, just Q. Number 5 over here. What about that one? That one is a little bit longer. Number 5, right? It should be this particular subtree, right? So that should be P implies G R. Basically this guy here. All right, good. P implies G R. We're halfway through. All right. Number 6, which will be this particular subtree over here. That should be G, basically GR. Let me see. Oh, that's actually crossing the subtree. Yes, go ahead, Thomas.
That's the middle of the subtree, so it would be not Q.
Yeah, that's a good question, actually. That's a very good point. If over here, if we got GR, right? Guys, you know what? I think because I modified the original example a little bit, can we do this? Let me revisit this next Tuesday with the complete saying. Let me revisit this, okay? I beg your pardon. I'll make sure I give you some proper explanation next time. We'll continue from here, okay? The problem is you cannot just go across somehow. Because we got some parentheses over here, so you cannot really say GR or something. You cannot.
That's kind of the question I was going to get to eventually, but can't you just, like, for now, just look at all the phi's and just what's under them?
Let me see. Maybe I'm...
Because the parentheses are induced by us, so you can never actually properly get the parentheses.
Oh, you know what? You know what? Maybe I look at the wrong thing. Okay, let me do it again. Sorry, maybe I was in... Let me do it again, sorry. Number 6, okay, sorry. I don't know what I was thinking. Let's be careful here. So number 6 is actually over here. Sorry. Exactly over here. I don't know. Somehow I thought it should be something like this. That's my bad, all right? Wow. Be careful. Don't be like me. Okay. Number 6 should be exactly over here, right? Okay, I should even cut that part from the recording so I don't confuse you guys. But bear with me, it's late. Part of the learning, I'm also learning, absolutely. Okay, number 6, let's write it down. So, not Q. Exactly this one here. All right, very good, thank you. What about number 7? Just P, all right? What about number 8? Be careful, number 8 here is going to be exactly over here, right? Number 8. That's going to be F. Well, thinking this way. Number 8 over here is simply, if you think about number 8, it's just to the left of the OR. So it's going to correspond to the entire left disjunct over here, right? F P implies GR. All right. What about number 9? Number 9 will just be this part over here. Okay, the consequence. Not Q and then P. What about number 10? Entire thing. All right. I think you guys are learning better than I am, which is good. Yeah, I'll take question. Just give me a moment. All right, good. Yes.
So if we were given a parse tree,
Yes.
but no formula,
Mm-hmm.
and we were asked to determine the formula from the parse tree,
Yes.
how would we know about parentheses?
Parentheses. Yes.
Because they change the meaning, right? Like
Yes.
here, the meaning of what you wrote for 10 is different than the meaning of what
Yes.
you wrote
Yes.
for the main formula.
Yep. Absolutely. I would say for the subformula over here, yeah, we ought to be careful. Yes. Let's talk about this one here. I tell you why you should write.
Even number 9.
Let's say number 8 first. Okay. Let's say for number 8 over here, let's take a look again. Number 8 is really about this one here. The safest one, let me draw the number 8 tree here, okay? I'll be very precise. Let's say number 8 is this particular tree. F and then we got P here, and we got G here, and we got this one here, and then we got this one here. Okay, this one here. Yes. So Patrick got a very good question. If we got this one here, if you consider, okay, if you consider this one I just wrote versus, think about star here, versus this original one, which is star star. They are not the same because if you didn't put any parentheses, we said that unary temporal operator should bind tighter. So FP should be considered together. Agree? On the other hand, in the original formula, we say that you should really talk about this one first before you apply F. So they are different meanings. Okay? So how can we be sure that the subformula that we give from the parse tree will have the same meaning? Number one, it's not in general possible to give exactly the same bracket as the original string if you didn't know what the original one is. Yes, I agree. Because you can bracket in many ways that will still give you the same meaning. Okay? So I would suggest the safest way is to bracket all the way. How? Thinking this way. F here is on the left, right? So whatever you get from the right subtree, bracket that. And then for P here, itself, you can bracket or not, doesn't really matter. Okay? And here, this is another tree, bracket that. And this one here, you may bracket if you want to. Okay? What's the point here? The point is you want to make sure the subformula you give have the same meaning as the original one. The bracket may be a little bit different, but as long as the precedence will still work out its way, the same way, you'll be fine. So let me write down. So star and star star are not the same because in star star, F is applied last. In the star over here, F should be applied first, right? Because it's unary. Apply first. All right, number one, we should know. We should really bracket properly. Okay? So what should we do instead? From here, let me put it here. Instead, bracket strings that's obtained from subtrees. Definitely. Okay, let's now continue with this. So the fixed one, so instead of this one here, we should really get F brackets over here, and then P brackets, oh, sorry, P implies brackets GR. Okay, so you can see the string here is not exactly as the original one because we got some extra pair of parentheses, but it wouldn't change the meaning because you got to bind GR together anyway. All right? Anything that's not clear? Okay? And this one here is fine. And this one here, number 10. Yeah, of course, you got to bracket that properly. Let me fix that. I want to make sure everything you write from the notes is actually right. So this one here, what you got to do is,
Number 9 isn't fine, right?
number 9 is actually fine. No, it's not. No. Number 9 here, let's look at number 9. So that means you got to say not Q, bracket together, which is a subtree to the left of the until, right? So what you should do instead is to say this. All right? I'll try to give you guys more exercises, so you can definitely practice. But today, just talk about principles and just one example. And this one here is going to be, this part here is the same as before. And then you can say not Q or P. Okay, like that. Chidalu.
So the main thing here is that even in the subformula, we kind of look at the original formula to put the brackets on.
Yeah, maybe just with some extra brackets, but the meaning, like an order of interpretation, should be the same.
Okay, but can't you just look at the original formula?
Oh, but the problem is, I might just give you the question. The question itself might just be the parse tree over here. I may not give you this to begin with. If I give you this to begin with, maybe when you guys get more and more familiar with the process, you may not even need to draw the parse tree first. You may not need to.
But you give us the brackets for the parse tree.
No. Okay. Let's say, how can I ask you? Let's say, two possibilities. I might just give you this only, in which case you have to give me all the subformula. In that case, you have two options. Either you can just draw some parse tree over here, but when you turn the parse tree, the subtree in the parse tree into the formula, you got to make sure you bracket properly, like how we discussed, number 1. Okay? Or you can also, based on this formula together, you can just try to find the individual boxes and then turn them into subformula. That's something I didn't really say, but you might just work out a way for that. Okay? That's question number 1. Another question could be, I just give you the parse tree directly and say, now work out exactly what the subformulas are. In that case, you have no idea what the original formula is, right? As long as you bracket in the way that we actually talk about, you'll be fine too.
So if you just give us a parse tree,
Mm-hmm.
we want to get the subformulas, but there's no bracketing in the parse tree. So I don't know the order.
Okay. Again, let me be very precise again. If I may, let me do once more, okay? Yeah, this is important, so let's clarify. And I think you guys asked the right question. Okay, let me be very precise about what you may have to do. Let's say just a parse tree, no formula, okay? Let's say. Yep. First of all, given a, let me get a little bit more space for myself. Given a parse tree, enumerate all the subformula. Right, that's another way I can ask over here. All right, so now apparently you can see in the parse tree over here, we don't have any brackets. But the brackets are implicit in the following sense. If you look at the subtree, let me just erase the phi so we can get better highlighting. Sorry. Let's take one for example. How do I work out the subformula from here? Okay, let's say that's one example, right? The way to see that is you can see that one there has 1, 2, and 3. 3 parse trees. Oh, sorry, 3 subtrees. 3 branches, all right? This is the first subtree. This is the second one. This is the third one. Okay so far? Okay, let me label them. Think about this one here is the first one. This is the second one. This is the third one. Okay? Implicitly, there is a bracket to say, in order to really work out the conjunction over here, the left operand should be whatever formula it is from the entire subtree over here. So there is an implicit bracket. Are we okay? Good. So if you want to work this out, you can think about conjunction here. Oh, you know what? Let me be consistent. Conjunction here, the pink. And what should be the left-hand side? It should be whatever this is. Of course, itself might contain some further subtree. You have to bracket further, right? This one, we are lucky. We just got FP. So you can just put it. But if you want to put F and then P, that's also fine. Okay? Jura? Oh, that's something. Okay, very good. Yeah, and then, Chidalu, question for you. How should we deal with this?
You just put
Q. In this case, we are also lucky because the subtree over here is not complicated, right? There's only one. But in case this is arbitrarily complicated, you got to put the parentheses here too, all right? So this one here is going to be the G, and you can put parentheses or not, like that. Okay? Again, the parse tree itself does not contain any parentheses. But when you actually come up with a subformula, you may have to do it to force the order of interpretation so that it's consistent with the original formula.
So I guess I'm trying to kind of take away. So when we have branches coming out from I guess a non-terminal node, those implicitly implied brackets around that.
Exactly. Yeah. To be more visual here, let me just do it here. Think about this is one bracket here. This is one bracket over here. This is one bracket here, and that's also one bracket. As if, yes. Yes?
I'm just curious. So would it be better to just like add as many brackets as possible?
Yeah, absolutely. You know, I would say in this case, you'd rather be safe than sorry, right? So you'd rather add as many brackets as you can, and then make sure. So that will almost guarantee the meaning should be the same as the original one.
Can you just like simplify the brackets just like always?
Yeah, of course. You can. That's kind of intermediate that you might take. You might just put as many parentheses as you can, and then if you want to simplify, go ahead further. Yeah, absolutely. All right, guys, as I promised, I'll give you more examples for practicing, but at least make sure you understand what I'm trying to say here. All right, very good. Before the break, I would like to show you something that's optional, okay? And then we can talk about semantics. Let me see if I miss anything. All right, you guys can take a look. Apparently, in my answer, I do put brackets over there, right? I think you guys are really good. Okay, this is something after the break, right? We're going to start talking about semantics. But what I'm going to give you as an example now is going to be optional for the course, but I thought it's good for your knowledge since we talk about parsing. Remember, I talked about in this course, we will always give you the grammar that's unambiguous, right? It's always not, it cannot be ambiguous in any way. But I want to show you one very classic example of ambiguous grammar. Again, this example is only optional. It's a little bit challenging, but I just want to show it to you for your information. We wouldn't stay very long on this, just for your information. This example here is very classic. Have you guys heard about something called dangling else? Dangling else. I'll write it down here, okay? Again, let me write down explicitly. Don't panic. This is optional, right? I will never put this question on your test. Don't worry. I'm only trying to expand your knowledge, right? It's called dangling else. Yeah, I'll get there, yeah. Dangling else is a very classic kind of a problem that people, when they design their grammar, they might run into this trap, okay? So I want you guys just to take a quick look. This is a grammar. We say a programming statement, like a non-terminal, can be derived into either, okay, think about if, then, also else. So these are all the keywords, like F, U, and etc. And the statement here is kind of recursive, right, like a phi. And the expression here is, you can expect there might be another rule that will go further. And also assignment here will be another assignment rule that will just go over here. Okay? Now, this grammar here is ambiguous, and it's called dangling else. I'll give you guys some quick questions to think about, and I'll also show you the solution. You can spend some time on that. Again, optional. Somehow this string, it is derivable from this particular grammar. However, this string over here can be interpreted by the same grammar in two different ways. Can anybody see that? I'll give you guys just 1 minute, right? I want everybody to think about it if you want to, but if you are struggling already, don't worry too much, all right? I'll just wait a bit, yeah. The question was, given that particular string, how is that possible to really interpret that string in two different ways based on the same grammar? I'm pretty sure you're awake. Me too. Me too. Yes. Yes. Yeah. Yeah. Go ahead. Yeah. Oh, Martin, I'll call you next time. Yeah. Go ahead, please. Yeah. 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 Exactly. Very good. Yeah, guys, don't worry if you didn't figure it out. I'll just tell you. Somehow, this else is the problem. That's why it's called dangling else. The else over here can be interpreted to be part of this if. If, then else. Or it could be interpreted as else as part of this if. If, then else. Both are legitimate ways to interpret this string. It's called dangling else, only for your information. If you want to dig a little bit further, this is one parse tree. This is another parse tree. They look different. This is how you prove that this particular grammar is ambiguous. Right? That's it. Okay, just for your information. Let's take a short break by taking attendance. After that, we'll talk about semantics. All right? So let's now take attendance. Because I restarted my machine, so I haven't reset it up yet. If you guys give me just 1 minute, please don't go away just yet. Just give me 1 minute. Guys, I believe we should be able to start a class right away. Let's see if that might work. Let's give it a try. All right, can you guys check in, please? Yeah, attendance, please check in. You should be able to do it. Good. Yeah, any trouble? Any technical issue? All right, don't go too far. We'll take 2 minutes break.
Well, it's gone now, but I wasn't
Oh, no worries. That's okay. Why don't we let you sign up? Yes. Do you have a pen? I might have a pen. Let me check. I might have one.
There's one there on the table.
Awesome. Yep. It's sorted by last name. Yeah. Yep. Thank you. Yeah, if you can sign again as well, please. Thank you. Thank you.
The specification for lab 1.
Lab 1? What about it?
There was a thing in invariant 4 that said a plus b plus c is equal to n.
Yes, yes.
So, okay, I had ideas about how to implement the n in there, but it would change what's in the specification. So every time I would update the amount of cars in the bridge, so let's say a is equal to a plus 1, I would have to add n is equal to n plus 1. So would that be correct or not in the lab 1?
I'm not exactly. You mind talking to me again? Maybe after class.
Sure.
We can. Yeah.
Okay.
Yes. Did it work?
So I did click on it, but then now it says I still have an absence. So for some reason it didn't work.
Okay. Why don't you sign up here, and then I'll fix that later. Yeah. Just find your name here, please, and then sign. Yeah.
Thank you.
Thank you. Oh, can you sign as well, please? Yeah. Please. Yeah. Very good. Awesome. All right, guys. 1 minute, please. All right, we'll resume in just one moment, please. All right, let's resume. We got about less than 20 minutes. I think we can do something, but whatever we can already finish, we'll continue on Tuesday. Okay. Right. So up to now, we spoke about syntax for LTL. Let's now talk about, given that the formula you're given is valid syntactically, how it can interpret its meaning. Okay. We're going to build up about the semantics. You need to understand something very important called label transition system. That's going to be the basis for formulating the meaning for each operator that we spoke about. Okay? And we will need a little bit of functions and relations back in 3342, but I don't think it's necessary to really go through that math review lecture again. We just do just enough so you can recall the details. We'll see how you guys can recall. Right, so let's now go for some formal definition, and we'll do two concrete examples together. And a transition system we call model M. Right? Think about this will be like a formal model for us to really run the model checker. Right? It's like a graph. And it's actually like a triple. You got S, some long arrow, and also L. All right? And let's now just clarify some terminology over here. For now, don't worry too much about this one. It's just for exercise a little bit later. Okay? Think about this one here. This will be a finite set of states. And if you try to recall what a state really is, it's just about combination. Okay, how about this? Values of variables. Depending on how many variables you might have, then the state space can be the more variables you have, the larger state space it might be. Right? Finite number set of states. And what about this guy here? Okay. This one here is so-called a transition relation. And this is the point that we have to have you recall a little bit about the math. Okay? Do you guys remember what a relation is? Any detail be appreciated. Something maps to something, I like that. Okay, good. Yes? Function is like a specialized form of relation. We'll get there, but just relation. Yes, I like it. Good, very nice. Okay. Guys, for now, just remember a relation is a set of pairs. Okay, over here. And the more formal way, when you see the slides, I'll help you understand what's really going on. The formal declaration for this transition relation is like this. This is a transition relation like a long arrow. Okay. It is a member of, okay, the set of all relations between the states. Okay. This notion over here is about the set of all relations on states. All right, you can see here we got S here and also S over here. And we'll see example. Okay. This L over here, let's talk about definition first, and then we'll see example. This one here, by definition, it goes like this. Okay. Okay. First of all, you can see P here. I say, when we talk about any model, like a label transition system, we should always talk about there will be a set of P. What's P? Let's talk about P first. A set of atomic propositions. which, I'll try to draw some connection to the syntax, which evaluate to either true or false. To true or false. Think about the P here is simply something like this. If you go back to the grammar, like the P here. Rather than a single one, maybe a set of them. Just a set, all right? All right, and now let's finally talk about this L. And then we'll do one formulation, and then we do example. You will see exactly how to make them more concrete. L here is something called a labeling function. I'm pretty sure this might be a new idea to you. It might sound a little bit weird, but let's talk about it. Okay? Labeling function. Well, it is a function as opposed to a relation, right? Let's see how it is declared. Okay? It goes like this. L is a member of, okay, given a state, it can map to a set of atoms that satisfy that particular state. So what I want to put here is a set of atoms that are satisfied by the state. Let me give you some concrete example. Let's say, for example, let's say the P here is simply, let's say we got some variable x. Let's say x larger than 0, and also x larger than 4. Okay, let's say we got 2 atoms over here. Okay? So the P here is simply a set of atoms which we want to check ultimately. We're interested in knowing whether or not they will evaluate to true on certain state. We got 2 atoms over here. And then what does it really mean? Given a state, by applying L, it's going to give us a set of atoms that will be satisfied on this particular state. What does it really mean? I'll give you an example. Just for now, let's say we have some state number 0. State number 0, let's say, and the x value over here is simply equal to 2. All right? Let's say we got another state over here, S1. X is equal to -1. Let me give you one more, and then we can work out. Let's say we got another state over here, S2. X is equal to 6. Don't worry too much about how these states are exactly connected. I'm just trying to explain to you how L should be operated. That's important first. Okay? Given 1, 2, and 3, each individual states can be the input for this L function. Okay, let's see exactly how to work out. Given this, what will be the L of S0? What will be the L of S1? What will be the L of S2? Each one of them is going to be a set of atoms that will satisfy that particular state. Okay? I'll help you with the first one. S0 over here, imagine that you're going to try each of the atoms here in P and try to see which one will actually satisfy. It could be none, it could be 1, could be more than 1. That should be a set in general. In that way, S0 here is 2. 2 larger than 0, true. 2 larger than 4, false. So only this one should be kept. All right? So I will put x larger than 0. All right? What about S1? Empty set, right? You can see -1 larger than 0, false. Larger than 4, also false. Empty set. All right? S2, apparently 6 satisfy both. I'm going to put x larger than 0, Also x larger than 4. Are we okay so far? But there's one missing puzzle here. I haven't really put what should be here. Question for you guys. That's a little bit pop quiz for what's back in 3342. Based on the example I explained to you guys, would it be correct if I say P? Is it correct or not? It should be a subset. Yeah, I agree. I agree. However, but I'm not going to bother you guys too much about the details. I just want to help you understand exactly the difference. If I put just this tells me L is a member of this particular notation. This notation tells me about the set of all possible functions between a single state and a single atom. But it's always a single one. Not necessarily. It's a set. Okay? Let me write it down. It's actually important, just in case you have doubts. If I say L is a member of S function P, okay? This means given A states, return a member in P. Apparently, this is not the right way to model that, because we got a set. Jora. That's the keyword, power set. Exactly. Oh, okay, good. Power set. I'm pretty sure you guys had lots of fun with power set last year. All right. I'm not going to trouble you about power set this term. Don't worry. I just want you to understand what's going on here. No trick, but you need to understand this. Okay. If I'm ever going to ask you any question related to power set, I'll let you know explicitly before the test. Don't worry. That's why I was thinking about whether I should really review that entire lecture about injective, surjective, kind of function. Maybe not. It's not necessary. Yeah. All right, let me recap what we have learned so far, and then we do some little bit formulation, and then we can do a little bit of example, and then we are done for today. All right. Recap. In order to really formulate a model as a label transition system, LTS. Oh, by the way, you should really know the difference between LTL and LTS, right? They're different, right? Otherwise, you're confused, okay? Label transition system. Whenever you talk about a label transition system, there are basically 4 components. Number one, you have the set of atoms that you're interested in knowing whether or not they are true in every state somehow, okay? And you also got a triple here. You got a finite set of states, and then you got some transition relation, and also you got a labeling function. There's one more detail I want to ask you guys quickly. Why is there a transition relation as opposed to transition function? That's what I want to ask you. Okay, let's see this. So let me just write it down here. So transition relation here. Okay. So this will be the states relation states versus a member of, let's say, this function S. Patrick.
Because the transition relation might not necessarily be 1-for-1.
Sure. You want to be a little bit more concrete? Yes.
Well, in order for something to be classified as a function,
Mm-hmm.
it's the total, what is it, 1-to-1, I think, is the
Mm-hmm.
minimum that a
Yes.
relation is to be classified.
Yes, exactly. So think about this. If I got, let's say, S0 over here, let's say that's a beginning state, initial state. Let's say we might got S1 over here, and also S2 over here, right? And think about what happened in the state graph generated in your lab number 1, right? This is definitely possible. From S0, you can either go to S1, or you can go to S2, right? Either way, maybe by taking different transition. How do we represent this as a set of pairs? It's going to be S0, S1, and also S0, S2. Now, by the very definition of function, every value over here can map to at most one value in the range, but it's not, right? So it's not a function. It must be a relation, right? It's a side note. this one, not a function. Sorry, say it again. No, we don't worry about surjective, injective. No, we don't need to worry. Yeah. Sorry, say it again. I didn't quite catch you. Yeah. So let me not bother you too much with the formal definition, right? So being a function means for any value, for any pair, let's say for any pair like this, if you have the same domain value, it can map to at most one range value. But it's not the case in this case because S0 is mapped to both S1 and S2. By definition, it's not a function. Okay, it must be a relation. Yes?
How does change S0 map to S0?
Yeah, that's okay because it definitely can have a self loop. Yes, in that case, you would just add maybe another S0, S0, similar. Now you can see S0 here is mapped to both S1, S2, and also S0. So it's more than one. So it wouldn't change. So it's just cannot be a function in general. It must be a relation to be more accommodating. Yes?
Is this transition relation just some concept, or do we have to define it when we're like defining a system in LTS?
Yes.
We have to specify what the
Yes, good question. Why are we doing this?
The last example, we didn't have to do that.
What do you mean the last example?
We gave with S0, S1, S2 with
Mm-hmm.
greater than.
Yes.
Like, what is our transition relation?
Yes. So the example I gave you guys over here are just to show you how you can use the L function. Of course, in general, you wouldn't talk about each individual state in isolation. There should be some transition in between. I can omit that part, but we'll get there. Yeah, so of course, it could be that S0 should be mapped to S1 and this to this, and this might be like that. Yeah, but for the discussion of PL, we don't need to know them. So that's why I didn't draw them. Yeah, all right. Guys, how about this? I'm going to, 2 minutes left, right? I'll tell you what's going to happen next time. So next time, please make sure you're prepared. Next lecture on Tuesday will be the last one before we draw a closure for the coverage of your written test 1. Okay? So I can tell you what I plan to cover. I'll give you a look ahead, and I'll let you go. Next time, we're going to talk about, based on this, we're going to use the transition diagram with different states to talk about what does it really mean for a LTL formula that's valid, that's syntactically correct. What does it really mean when it satisfies some label transition system? That's something we'll try to do. But I'm going to give you an example as we define the operators. And we can cover next operator, also G, and also F, and also until. That's what we'll do next time. All right? Please get ready. Make sure you sleep well before you come to class. Yeah, please, right? All right, guys, thank you so much. Have a good weekend, and then you will see your lab number 2 by the end of Monday.